So I'm going to talk about lab experiments today. So the first question to ask is, why should we even think about lab experiments? So there are a bunch of advantages for lab experiments that are true not only for networks, for many other realms. So lab experiments allow us to control many aspects. One important one in the context of networks is that we can vary networks, whereas in the real world we usually see one instantiation of a network. But we can also control payoffs, information, node characteristics, and so on. It also allows us to focus on particular layers of a network. So usually when in many empirical studies you'll see one particular aspect of the network, say a particular friendship network, but not necessarily other layers of the network, like work colleagues or co-authors and so on. And we don't really know which one might matter the most. So here we can focus on only one layer and not worry about that. And one big advantage of experiments is that it's a cheap way to try new policies. So if you think about introducing a new advertising strategy or a new vaccination strategy, this is a cheap way to get insights into how effective it might be. So these are reasons why we might want to do that. There are essentially two approaches in this literature. So one approach is to actually impose the network or have the network formed in the lab. And that relates a little bit to the last study that Adam was talking about, where they implemented a particular network and looked at the learning process over it. The other approach is to elicit the network from the data, so look at an organic network, and then run experiments on the individuals using the network information in some sense. So these are the two approaches. And my plan for today is to give you a sample of experiments of both sorts. So my goal is to go through 3 experiments, and if I have time, then I'll go through a 4th. But I'll start with networks that are constructed in the lab and are either formed in the lab or are given in the lab, and strategic interactions are studied on them. And then I'll show you one experiment in which the network was elicited and experiments were run over it, on it. A word of warning. Network experiments are in their inception, and in many ways the methodology is still being developed. So I have time to show you only a sample of experiments, and unfortunately I will have some issues with the designs of these experiments. But you should be somewhat forgiving despite these criticisms, because these are some of the first experiments. And it's exciting in a way because there's a lot more to be done, clearly. All right, so let's first think about imposing or forming networks in the lab. So the advantage, like I said, we can focus on one layer of networks. There's no issue of missing observations or errors in eliciting the network itself. And we can study the impacts of very different network architectures, which we often can't do with real data. The disadvantages are that there's inherently small networks. So most computer labs have 20 to 40 computers. That really restricts you and how large the network can be. And this is...
You can network
Yes, you could. And with online platforms, this might actually be changing rapidly. So in the future, we might be able to do more. But as of now, it's still, there's no infrastructure. Yes, great idea. This is particularly important if we want to study repeated interactions or incomplete information, because you have a very small network, and in some sense, incomplete information we would think is more relevant when you have a very large network. And like I said, online platforms, networked labs, etc. are the future. So the first paper I'm going to tell you about is one in which the network is formed in the lab. It's one of the first and classical ones by Hori, Riedel, and Uhle. The underlying model is based on Bala and Goyal. I'm not sure we covered this so far. It's essentially an idea of unilateral costly linking. So in the Jackson and Volinsky paper that we saw, there were bilateral agreements to form links. Here there will be unilateral, and I'll show you a sketch of the model in a minute. And we want to essentially understand whether equilibrium networks will actually emerge, whether the predictions of the model hold water in the lab. That's the goal. All right, so here's the underlying model for this experiment. So there's a collection of n agents who form a network, and each agent j is associated with a value vj. So you're born with a value written on your forehead. At the outset, each agent decides which agents to connect to, and this decision is made simultaneously. Okay? And each link creates a cost that is dependent on the individual. So if I form a link with Sergio, I pay C Leeat. If Sergio decides to connect with me at the same time, he pays cost C Sergio. However, there is unilateral linking. So whether I decide to connect with Sergio or Sergio decides to connect with me, or we both decide to connect with one another, our ultimate benefits will be the same. The link will be formed. So we don't need an agreement by both sides to link. Okay? So this is the assumption here. All right? So this is in contrast to this pairwise stability that we were discussing. So the benefit of agent I from agent T, ultimately, once the network is formed, because once everyone decided on links, we have a network, and the benefit of each individual I who's connected to individual j depends on the value of j and the distance in the network between them. Where I'll use the notation that if they're disconnected, the distance is infinity. So let's suppose that person, Mr. I, decided to connect with n sub I individuals. Then the utility for them will be this discounted sum of values of everyone they're connected with. And the discount has a power that depends on the distance. So further people away are discounted. My direct friends give me more than my second-degree friends, etc. Minus the cost of linkages. So it's the number of people that I chose to connect with times the cost. So here, in a way, there's no reason from an efficiency perspective for two people to connect to one another because they both experience the cost, but the benefits are the same. So it's more efficient for only one to connect. Yeah? So this is kind of the first observation. In equilibrium, we would expect no two-sided links unless we're looking at some mixed equilibrium. All right, so how about information? In the underlying model of Bala and Goyal, information was complete. So everyone knew everyone's values and costs, but we can think also about incomplete information, which will be implemented in the lab. So think about a situation where these values and costs are drawn from some distribution. And you can think then about two contracts, one in which you know exactly the realization of this distribution. So this is just, you know, everyone's values and costs. The other one is that you know your own value and cost, but you don't know other people's values and costs. Okay? Yes?
Could there not still be mixed equilibrium?
In principle, there could be, yeah. We'll focus on pure, but in principle, there could be. All right, so the experimental parameters. So the parameters are as follows. There were 6 people in each group, so this is our n. So notice it's a small number. And parameters are chosen to generate stars in equilibrium. So they're focusing on very particular types of networks that emerge in equilibrium. The values are either what they call normal or high, and the costs are either normal or low. So I'll soon show you the precise parameters.
So parameters chosen to generate stars means like there is one with a very high value. Is that essentially what it means?
Right, exactly. So there will be some heterogeneity in some networks.
VIs,
Yeah. So I haven't told you yet how it's distributed. I'm just talking now about the values from which it's drawn. Yeah. Yeah, but heterogeneity will play an important role here. Yeah. Delta is fixed at 3/4. This is how much you discount the distance from individuals. This 3/4 is just designed to generate utilities that are integers. I'll soon put it on the board, in fact, right now. So here are the overall parameters. These costs and values are in terms of tokens, so I'm not sure what's the rate of transfers to dollars, but you shouldn't take them literally. But here is a normal agent. So a normal agent has a cost per link of 24 and a value, this V, of 16. A low-cost agent has the same value but a lower cost. And a high-value agent has the same cost as the normal person but a higher value. Okay, so these are the three types of individuals that they'll consider in the lab. And so the benefits from connecting to these sorts of agents are given in this table. This table does nothing but multiply by delta, delta squared, etc. So essentially, if you're thinking about a normal or low-cost agents, for example, they have a value of 16. So if you're distance 1 from them, you get 16 from them. If you're distance 2, you get 3/4 times 16, which is 12. This is 3/4 squared times 16, etc. So you see that that delta equals to 3/4 leads to integers here, and that's why it's picked in this way. All right, so here are the different treatments. They have a lot of acronyms here, so I'll try to keep track of them for you. So one type of treatment was one in which there were 6 normal people. So O stands for normal. Another treatment had 5 normal people and 1 high-cost individual. Another had 5... Sorry?
1 low cost.
Low cost, thank you, yes. And 1 low cost. Another had 5 normal and 1 high value. And one had 4 normal people, 1 low cost, and 1 high value. Okay? So whenever you see C or V, it means that there is either 1 low cost or 1 high value. That's what the C and the V stand for. B is just the benchmark or baseline. CV means that there is 1 of each, low cost and high value. The I stands for information or complete information, and the N stands for no complete information. Okay. And in the lab, incomplete information means the following. So they knew the distribution of people. They knew, for example, in this treatment that there were 5 normal people and one low-cost individuals, but they didn't know who was whom. Okay? So if you're the one with the low costs, you know perfectly what are the types of the other individuals. But if you're not, then you don't know who is the low-cost individual. Okay? All right, so here are the dry procedures. The experiments were run with over 200 subjects in both Amsterdam and Los Angeles. Subjects participated always in one particular treatment. So if you came to the lab, you saw only one treatment. And you participated only in one group for 30 rounds. This is something that will be important in a second.
Treatment means composition and incomplete.
Everything. So exactly. So everything was stuck. So including your type and your label. So when you came into the lab, you got a label of A, B, C, D, and E, etc. That thing was stuck with you for all 30 rounds. In addition, your type was stuck with you for all 30 rounds. Okay? So this immediately should trigger a question of, are we introducing here repeated game effects? And this might be important here. Because in a way, there's you could conceive of arrangements that might at least lead us to fair outcomes. So I might decide that today I link to Elchanan, and tomorrow Elchanan will link to me, and we'll start alternating, and we'll get equal payoffs in the end. They actually phrased the normal, low cost, and high value in terms of colors. You don't want to tell subjects they're normal or abnormal. And the average payment was $25, which is fairly standard in experiments.
It's per round or for 30 rounds?
For 30 rounds. Yeah. Per round, it would be very high. Okay. Now, at each round, subjects were informed of at the end of the round, they were informed of the network that was created, the benefits that they got. the costs and the payoffs and the overall payoffs. So I find this a little bit odd in terms of the incomplete information. It's something to note here, because in a way you could learn fairly rapidly who is whom here, given that everything is fixed throughout time. So when we think about incomplete information, one needs to take this with a little hill of salt. All right, bless you.
So they know the network. Oh,
Yeah, so they see basically
so they know
every
exactly all the
exactly,
distances and
exactly,
they put
exactly,
them in reverse.
exactly, exactly.
So they're informed of not their own benefits, but everybody's.
No, they're informed only of their own benefits, but
So
even
how
that.
can you learn other people's types except for through the network structure?
Well, because if I know that I'm in a setting where there is only one high value person, and I'm connected to someone and I see that I get the high value, that's it.
And you know that you got that from somebody distance 3, then you know.
Yes, and in a sense, given that it's running for 30 rounds and they're paying for all 30 rounds, you have an incentive to use the first round just to link with everybody to see what you get. So your incentives are kind of biased here. All right.
If you link with everybody, you'll see nothing.
No,
You'll-
if you
you'll not
link
be able
with
to-
each one separately at each period, right?
So
I'll link with
then you
you
need 5
today.
rounds for that.
Exactly. 5 out of 30.
Okay.
Yes.
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 Do they get a feedback after each run?
They get feedback after each round. Yes.
Did they, by the way? Or
Sorry?
were
They
smart
did.
enough to do exploration in the beginning?
They don't report this. Yeah, so I don't know. But we'll see that there is some difference between the first periods and the last periods. The Bayesian and Nash equilibrium prediction, so Bayesian refers to the incomplete information, Nash to the complete information. They all generate stars or quote-unquote connected stars, so basically 2 stars that have a bridging link between them, or the empty network in one incidence. So I won't describe this fully, but let me just give you a couple of examples. So here are the networks that corresponds to the benchmark treatment where everyone is normal, and the high value incomplete information treatment. And here you see one network that has a star and one that is the empty network. These are 2. Yes.
So you're supposed to do the idea that you can, if you know the cost, you know who's supposed to be the center of the star, or is it a coordination game to figure
It's a
out?
coordination game, effectively. And it's
That's a normal case. Everybody's normal here, right?
everyone is normal, right? But in general, so in the next example, for example, these are equilibria that correspond to low-cost individuals, where you have one low-cost individual, and the equilibrium puts the low-cost individual in very particular locations, right? So there is a lot of coordination that needs to happen here, both because there is multiplicity and because you need to figure out where to put this person, even if you agree on the equilibrium. Okay, so like I said, there's multiplicity, and this is something that in general in experiments we don't love, because whenever you have multiplicity, you're imposing a coordination problem on top of whatever you're looking at. So if we don't see an equilibrium selected, we don't know whether it's coming from them not being able to coordinate, or whether it's coming from them not understanding the strategic incentives of the game.
But they might be playing mixed equilibrium as well, also.
They could, and that's completely ignored.
But even for the same graph, who is going to pay for the link? That may be kind of
Whoever, exactly.
one or the other.
Yeah,
It's
some,
nobody-
exactly,
it
exactly,
doesn't say.
exactly. Some of them do,
Some
but some of
cases,
them
yes.
do, some of them don't.
So,
Yeah.
so what's the goal of this?
The goal is to see whether that you see stars. So like I said, these are exploratory experiments. So here is the frequency of equilibrium outcomes, and like all the discussion, the discussion is leading to these results. Essentially, I personally don't find it particularly surprising that we don't get a huge percentage of equilibrium outcomes here. One thing that is somewhat interesting is to note that the percentage of equilibrium networks that you see ultimately is substantially higher when you have agents that are quote-unquote focal. And for some reason, high-value agents serve as more effective focal agents than low-cost agents. So heterogeneity seems to help, and it's very particular heterogeneity. I'm not sure why.
But this shows that it's all coordination problem because in the basic treatment there is 0%.
Yes,
So
yes,
it's all about coordination.
yes. Or not. Yes, we don't know.
I mean, if there was excellent
Yes.
coordination, we'd see something, some equilibrium outcome.
Yes. And you could also ask what happens if we consider, maybe we're getting very close to equilibrium, but we're just not hitting it perfectly. So you could think what happens if we consider outcomes that are almost stars, and in that sense, you need a change of only one link. So either to sever a link or to add a link or to shift the location of a link to get an equilibrium network. And the results actually don't change. So it's not even close to an equilibrium outcome, at least not with respect to this measure. Looks at the frequency of star networks, and this is too narrow for some reason. This is the first 10 rounds, and this is the last 5 rounds, I think.
So you are looking at distance in terms of links. How about distance in terms of
Payoffs, they don't look at it.
That's a better
Yes.
measure because maybe
Absolutely.
it's close,
Absolutely, yeah.
You want epsilon equilibrium for small
Yes.
epsilon, not the...
Yes, we'll need to write the authors. Yes. Mhm. You had another question? Yeah. Yeah, there are different ways by which you could measure this, and that's the only one they report, unfortunately. So this is the last rounds. These are the first rounds. I won't focus on these particular classifications of the types of star networks. The only thing to glean from this is that there is substantial increase in the number of the percentage of star networks as you progress in the game. So actually, in these treatments, we actually do get fairly high frequencies in the last rounds of equilibrium outcomes. So at least it's not complete noise. And again, this learning seems to occur only when we have some sort of focal agent.
So what you're showing us?
This is,
The
yeah,
last
unfortunately,
five
it's,
rounds.
yeah, exactly,
Last 5 rounds.
yeah.
So you get up to 90%.
Exactly.
Even a very specific equilibrium.
Exactly, exactly. So this is actually kind of interesting to me that they managed to do this, but the mechanisms are not very clear. Yeah. Okay. The last thing I'll show you from this experiment is what they call the stability of the network, and this is to me quite surprising. So they look at the relative stability at time t, which is the fraction of agents who don't change links between round t minus 1 and round t. So they do the same thing they've done in the last period. And here's the figure. So they divided it into blocks of 5 rounds, and you look at the network stability, this fraction, and we see a clear split in treatments. So these are the quote-unquote good treatments where we have the focal high-value agents, and these are the other ones. And we see a fair bit of stability toward the end. Okay. Now, if they're playing close to equilibrium, they're close to best responding. So in some sense, they don't have great incentives to change their actions. But it's still kind of interesting that they stabilize to such an extent when they're far from an equilibrium.
Unless you get the repeated gain
Unless,
phenomena,
yes,
where they keep,
exactly.
switching,
Exactly.
alternating, I mean.
Exactly, which you would want to check
that's what
for.
the point
Yeah.
was, I don't know.
Yes, yes. So some of the issues I
It should be 0. The alternating would be 0.
yes,
No. So point five is not bad.
yes.
Unless they alternate
On
on
cycles.
When you say 1 to 5 is an average of 5 data points. It's
Exactly.
not if there has been at least a
Exactly.
change in 5 periods.
Exactly. Yeah. Yes. All right. Okay. So the main thing to glean from this is that with homogeneous agents, the equilibrium predictions here fail completely. But again, we don't know whether this is driven by other effects or because of the agents not understanding the strategic incentives. Heterogeneity helps a lot. And it's interesting to understand kind of how what determines focal agents here. But again, there are many caveats to this paper. Now, there are several other papers that study unilateral connections. This is probably, yeah.
Information as we proceed across routes, does the low cost or high value agent remains the same?
Yes. Yes.
So technically, at like round 30, I know who it is.
That's, yes, exactly. Exactly. In principle, I mean, you don't have to, but you could very easily. Yeah. And you know, they could actually check for that, right? Because in principle, if you saw the data, you could see if you had enough information to infer that. So this is something that if we dug into the data, we could actually check how frequent that was. Right. So there are several papers that are in the same style. There are a few papers that are now coming out that try to study experimentally bilateral connections. They're for a very particular linking protocol. For a reason I don't understand, they usually impose these very particular protocols and are more focused on selection rather than understanding the basic question of what are conditions for stable outcomes to emerge or which ones will be selected. But it seems like a very interesting direction to take. In fact, I think it might be interesting to think about designs that have more free-form interactions and just check whether we get stable outcomes and which ones. And this would be akin to studies that we've already done years ago on assessing the core in both general equilibrium and matching markets. And if I have time in the end, I'll show you some model of an experiment for matching that I think could translate to this sort of setting. This would be very useful to know, actually, because if we knew that in the lab we actually get stable outcomes, this might give us some justification for econometric studies. Because in principle, if I look at a network and I want to estimate preferences of individuals over networks, one strategy is to assume that the network is stable, and stability gives us a lot of constraints on preferences, and use these constraints to estimate preferences. And Matt mentioned that this does have issues because you do have multiple stable outcomes, so you need to think about that a little bit carefully, but it still seems like a promising direction. All right, so the next type of experiment I'll talk about is one in which the networks are imposed in the lab, but we're looking at a strategic interaction on the network. So I'll describe a particular experiment that was published 2 years ago that looked at network games. So this will be very related to the types of models that I told you about yesterday afternoon. So the idea is to vary both the payoffs, whether they're complements or substitutes, and the information, whether it's complete or private. And in addition, we'll look at different networks. So here's the basic design. So there are 3 different 5-person networks. So these are even smaller networks. What they call the orange network, the green network, and the purple network. Notice that they differ in how connected they are. So the orange network is the most connected here. Each player can decide whether to be active or inactive. And being active costs a fixed cost, which in the experiment will be set at 1/2. Okay? So how do we implement complementarities here? Strategic substitutes will be essentially this experimentation game that I showed you yesterday. Or this is a game that's often referred to as the best shot game. So a player earns 1 if either she or one of her neighbors is active, and she earns 0 otherwise. Strategic complements will be implemented by assuming that an inactive player always gets 0, and an active player earns A times the number of active neighbors. Okay? So the more neighbors you have who are active, the more incentives you have to be active yourself. So in that sense, it's a game of complementarities. And in the experiment, this parameter will be 1/3. All right. So with complete information, everyone knows the realized network and their own position in the network. With incomplete information, this is what was done. So the probability of the orange network is P, and the probability of the green or purple networks are divided equally amongst the remaining probabilities. So each of them has a probability of 1 minus P over 2. In the experiment, they either made the orange network the most networked network, very unlikely with probability 0.2, or with very likely with probability 0.8. Players are randomly allocated to the 5 nodes of the realized network, and they know only their degree. So they know the structure of the game, they know the distribution, they know the networks that might be happening, but they know only their own degree. So they don't know where they are on the network or which network was implemented. So a symmetric strategy profile then just specifies what you would do if you are degree 1, degree 2, or degree 3 in this network, which are the only possible degrees. All right. So here are the theoretical predictions. I won't go over all of them, but I'll tell you what the important thing to glean out of it. So this is focusing on pure equilibria for complete information. So we see here a lot of equilibria that vary in the number of active agents. So for example, let's just look at the orange network. So here, this is complete information. So you know precisely the network and where you're at it. So if we look at the orange network, in the case of substitutes, we know that adjacent nodes in equilibrium will not be active. So therefore, we can either have A, C, and E be active, or B and E be active, or A and D be active. Okay? And this is how all of these equilibria are constructed. So again, here we have a selection issue, and they will actually use it in their favor in the sense that they will get equilibrium outcomes, and they'll suggest that some equilibria here get selected more frequently and are more appealing for a variety of reasons. For substitutes, things are nicer in the sense that there's a unique equilibrium when there's incomplete information. When there are complements, there are multiple equilibria, at least when the orange network is fairly likely. All right. Okay, and again, we have this problem of a coordination game that's imposed on a network game. All right, so here are the drive procedures. So this was run with 240 students in the University of Innsbruck. This is a free software that's fairly easy to work with, in case you get interested. There were 12 sessions with 20 participants each, and 2 sessions for each of the 6 treatments. Okay? So we have complete information with substitutes and complements, and then incomplete information with substitutes and complements and the 2 probabilities for the likelihood of an orange network. Now in each group, the 20 subjects were split into 2 matching groups of 10 each. This means that between these groups of 10, they didn't see one another. So it's as if you invited 10 people in an isolated manner in the lab. So this is just to increase their number of observations. But the shortcoming of this is that you have a random rematching within a group of 10. And this means that you're meeting the same person in a very likely multiple times. This was run 40 periods, so this is why I'm saying that it's quite likely. The average payoff was 16 euros plus 5 euros show-up fee. So they were not too generous. All right, experimental feedback. So at the end of each period, in the complete information, they saw the neighbors' decisions and the resulting payoffs. In the incomplete information, they saw the realized network, their own position, the number of active agents, and the resulting payoffs. Yeah?
So the whole experimental design is also transparent?
Everything is transparent, yes. And this is generally true for experiments. So one thing that distinguishes economic experiments from experiments that are run in several other fields is that We don't like to deceive subjects. So whatever you're doing, you're supposed to tell it to be transparent to the subject. Yeah.
Across the round, you are going to stay in the same position in the network?
No. So here everything is random.
I can
Yeah.
be see in one round and
Exactly. Exactly. Exactly.
When I'm sitting before the computer, yeah, that I don't know are my neighbors in the same group or the others.
Right.
So
Exactly.
the structure is not a physical connection, yeah, but
Exactly.
some people over the internet.
Exactly. So here, I mean, they're trying to control for these repeated game effects. So in that sense, I think it's the right way to go. The fact that they're rematching with groups of 5 out of 10 for 40 periods means you'll see people again and again and again, and you might learn. In principle, you could learn something from their behavior, but there's limited communication here.
And it's anonymous, right?
It's anonymous. Anonymous. They're sitting behind computer screen. They don't see each other. No, no,
They don't
No.
know they will group with
No.
this round.
no, no. And this would be much more of a concern if they talked with one another, because then you might learn of a style of communication. But still, it's something to worry about statistically.
They can't see the neighbor's screen and see that it's the same.
No, we usually have these,
Okay.
and I think they even report on that in the paper.
Since after each round is rematched, the group is rematched, then what's the difference in complete and incomplete information? Because since the group is rematched, you don't know next round you are facing different person. So,
Yeah.
So what's the purpose of complete information?
Yeah, so you're right that, and this is a nice point about experiments in general. So they're talking about incomplete information in the sense of which network is realized. So in the complete information, you know the orange network, you're playing in the orange network. In the incomplete information, you don't, right? In general, you can still think about incomplete information about the distribution of play in the population. So maybe I'm sitting in the lab as a subject, and when I see my payoffs, I'm learning something about how other people are playing. So there is kind of a meta-learning about my opponents. And that's not something I'll discuss here, but it's something interesting to think about. All right, so here's a messy table, and I'll tell you what to take out of it. So this is the frequencies of being active in the complete information game for each of the networks. So let's see what it tells us. So if we focus on this panel over here, so this is the orange network, and recall that there are all these constellations of non-adjacent nodes who were contributing. So for example, we had A, C, and E contribute, or B and E, or D and A contributing. And what we see here is a pretty pronounced effect where A, C, and E are contributing with a very high percentage. Right? So what you see here is a fairly 91% of the E are active, 68% of the C's, and 95% of the A's are active.
A and D are the tops, no?
Exactly.
Yeah,
A and E
okay.
are the two tops.
So
Yes. Yes.
they can count on themselves.
So the equilibrium in which A, C, and E are active prevails, and this is in fact the case for all of these networks. And what they say is that this might be selected as an equilibrium because it's robust to mistakes in a way. Because if A decides not to contribute, she's only hurting herself. B will still get the benefit through C, right? Whereas if let's say only A and D contribute, if A decides not to contribute, now B is fragile, because if A decides not to contribute, then she remains, well, here she'll be a partner with D, but at least here she will be more fragile. So that's the explanation. Of course, with the orange network, it's a bit trickier because this fragility explanation doesn't quite work, but this is the explanation for why this might be an equilibrium that they're drawn to.
Is there anything on whether once they're in equilibrium they stay there?
No, not that I've seen in the paper. That would be interesting, like whether they alternate. Yeah. I mean, in here you see such a high frequency of selecting this particular equilibrium that, just statistically it can't happen a whole lot, but it might be interesting to look at the dynamics more carefully. They might. On D?
Yeah, put D, and then C and E don't have partners.
Right. So the DNA, right? Yeah. You're right. Right, but yeah, you still need. Yeah, yes. I won't say much more. Yeah, that's a good point. Yeah. All right. With complements, the unique equilibrium is played for the green and purple. So recall that when there were complements, there was a unique equilibrium for the green and purple network, but a multiplicity of equilibria for the orange network. And the unique equilibrium is actually played in the green and purple networks. The efficient one is played for the orange network. So we see here different selection criteria that are sort of interesting to think about more generally. So here we are thinking about robustness to mistakes, and here we're thinking about efficiency that's driving results. All right, let's look at incomplete information. So here we see, again, a very pronounced selection. So we see here that, for example, with substitute and p equals to 0.2, the person with degree 1 almost always contributes. So remember that with substitutes, if I have a low degree, this means I don't have very many agents, so I'm more likely to be active. So in fact, in all of the equilibria, the person of degree 1 always had to be active, while the person with high degree could rely on their friends and never had to contribute. And we see something of this sort. So in the extremes, we actually see behavior that's fully in line with equilibrium. In between, it's not quite the extremes that equilibrium would require. So subjects play fairly well the unique equilibrium, absent these degree 2 individuals. And one nice thing is that the comparative statics, at least, of the equilibrium actually holds. So the probability of being active here decreases in degree and increases in terms of connectivity when we shift between networks. So the fundamental comparative statics of these models holds, at least in this particular setting. With lower connectivity, we see a similar result. So the comparative statics are in line with equilibrium predictions, and play is quite consistent with equilibrium as well. So this is a case where we get a fairly good confirmation of the theory. Okay, I'll skip that. This is just to see the learning in these markets. And this is something that you always want to see when you run an experiment, because in the first rounds, you don't know what's happening. Subjects might be learning about the interface itself, who knows. So it's very useful to sometimes split the data and see whether there is substantial learning to be observed. So here what we see is the fraction of groups in which everyone coordinated on a particular equilibrium as a function of the period between 1 and 40. Okay? And what you see is that these are increasing. Okay? That's the only thing to note. They're learning how to play these. Same thing for the incomplete information. This looks steeper just because the graphs are narrower. No, these are just the experimental rounds. So there were 40 actual periods of the experiment, and that's what it's looking at. Yeah. Okay. Now we can look at the different degree individuals. So notice that we saw this already in the aggregate. The degree 1 and degree 3 individuals get what they should do very well here. The degree 2 people, they're a big blob of mess. And there doesn't seem to be much learning going on here. So this is kind of interesting to think about. For complements, there is actually some learning going on. I'm not sure why that is. In part, at least here, there are multiple equilibria, so this might be messing things, but they actually look fairly similar. So I'm not sure why the patterns are a bit different. All right, so one thing that I think would be interesting to see is whether the subjects are actually best responding to what extent are they best responding to the experimental distribution of play. And this is something that is often useful in experiments. So we often compare behavior that we observe to equilibrium behavior. But each subject has to think about the distribution of actual play in the lab, and we would want to understand to what extent they're best responding to that as well. Again, the comment on multiplicity and mixed equilibria is always something to worry a bit about, although in these experiments we actually see very nice selection, so it seems like we didn't just get noise. Here we saw a difficulty in coordination that generated these quote-unquote robust outcomes, at least for substitutes. And when you have these small networks, a natural thing to think about is why don't they just talk with one another and figure out what they should do, which is efficient. So if we're connected, isn't part of the connection just communicating with one another? So this is not a criticism, it's just something that might be interesting to explore in the future. It's also a very small network. So if we think about applications, if you really think about settings in which you interact with very few people, the assumption of incomplete information might not be the best one. Because we might have, if you think about even your class in your class in grad school, you might have a pretty clear idea of who is friends with whom. And reputation effects are something to worry about as well. There are several other experiments on specific games. This is a mushrooming literature. There's a very nice new paper by Marina Agranov and Matt, who will hopefully mention it next week. There are experiments that come from computer science that show that sometimes very difficult problems, like graph coloring problems, can be solved very easily when you give local incentives by individuals that get local incentives, where, for example, I get paid if everyone around me has a different color than me. You model me as a country, and you give me a payoff only if my neighbors have a different color. There are also a bunch of experiments on learning on networks, and Adam talked about this extensively, so I won't mention that, but there are a bunch of references here. All right.
What do you mean solving difficult problems?
Difficult.
No, I don't think that's what they...
That is kind of what they mean. It's kind of fake NP hard in the sense that once you fix the size of the map, it's not hard. It would still take me a long time to just look at the graph and color it as an individual. But as it turns out, once you allow people to make dynamic choices over the color, so think about a network. Each person has a choice of colors and they can switch at any time. And once the network stabilizes, or after a certain time, I'll pay each individual only if their color is different than everyone else's.
Well, if this works, you can emulate it. Yes.
Absolutely.
And that means that's not difficult.
Absolutely, absolutely. So this is why I didn't present that, but absolutely. In principle, this.
In whichever way you. Yeah.
Yes, I'm not.
What is the answer?
What do you mean? There is no answer. I think you're absolutely right. You don't. Then
it's not difficult. Yeah.
Oh, so they phrase it. Sorry, this might be my phrasing. They phrase it. If you look at the paper, some of these papers will say, "Look at that. We take a problem that, in principle, we thought is very difficult. We put it in the lab, and in 3 minutes, it's solved." Now, you're absolutely right that once you figure out the algorithm and it works, I could simulate the sequence of best responses. And if I can simulate it very quickly, it's not difficult. And I completely agree. I'm not sure. I'm not saying we need to run these experiments. I'm just saying there is this literature.
Okay.
You don't have to like it.
No, it's okay. We made the point. Okay.
Yes, I think we agree.
Look, if you raise the word difficult there, then it's okay. Okay.
All right. So in general, let me just highlight some of the challenges with experimental games on networks. So the first thing is this curse of multiplicity, which is common to many of these games that we study. And in the lab is really problematic because we're always dealing with a coordination problem that's layered upon whatever is the strategic interaction. And the other thing is the small networks problem. And this is difficult both because it's at odds with some things that we might want to assume, but also because if we want to try out different networks, the numbers explode very rapidly, and this we saw already. So we're sort of restricted to these small networks in order to try many architectures of networks. It's because the problems are often complex, it's also often very difficult to disentangle whether subjects are just using simple heuristics or they're misunderstanding strategic incentives or they're misunderstanding the game as a whole. This is something that's true for any experiment, but I think it's arguably more severe for these cases. It's also very hard to control for known biases. So for example, we know that in the lab, people tend to be altruistic and tend to like fair outcomes. But once I start thinking about whether it's driving my results on a network game or not, I need to figure out what is the reference point. So if I wanted to generate control treatments that would see if my results are driven by fairness, say, I would need a lot of control treatments. And this is a difficulty as well. All right, so the last type of topic that I wanted to talk about are experiments that are run on elicited networks. So this is when you have a network that you elicit, and then you run experiments on the participants of the network. All right, so a note on subjects' populations. First of all, many adult populations are very problematic. So we're actually very bad subjects. So you know, one instinct is to say, there are so many online social networking platforms out there. Why can't we use that data? It would be for free because they've already collected it. So we can use Facebook, Instagram, whatever. The problem is that we don't really know what a link means. And it's very hard to actually assess the strength of the link. So people have come up with clever ways, and you can track, for example, number of messages on Facebook, frequency of messages, etc. But still, the people who are closest to me are not necessarily, I don't communicate with on Facebook, for example, personally. So that's one problem. The other problem is that as we grow older, we become more complicated, and we have many layers of interaction. So I have people that I work with, I have people that I co-author with, I have friends, I have family members, and so on. And this is just an illustration of one such example from our world. So this is from a study that was done on a professional school in Los Angeles. And this is just a division by departments in the school. So the shapes correspond to different departments. Gray is male and white is female. This is the research clusters within each department. So this is one layer of the network in principle. This is the co-authorship network. Here is the friendship network that we elicited using a survey. And the dark links here are the composite links. That's when you have both co-author and friend. And what you see is that the correlation here is positive, but it's nowhere close to 1.
So go to and fight when you don't have.
I don't think it would pass IRB. All right. So one solution is to use special populations. So for example, children are very useful because if you look at them in school, it's arguably much of their interactions happen through their school interactions, and I'll soon show you a study that did just that. You could think about undergraduates in a university where that's basically their life. They still have friends at home possibly, but that's most of their social life. You could think about villages in developing countries, and we've seen a bunch of examples of that, where you have a population that's restricted in size, and you can map the whole interactions within that population. So that's one type of solution. One note on network elicitation, because it appears a lot in these sorts of studies. So in many studies, kind of my impression is that the 60 to 70% is roughly the percentage of links that are assessed as bilateral. Now, in many elicitations, the way they're done is by asking for the k closest friends, where k is not always very large. It can be 3, it can be 5, what have you. Now, suppose that k equals to 5, and we talked about this a little bit yesterday. If I have 3 friends, one of whom has 10 friends, so suppose that I'm friends with Adam, I don't have any friends, but Adam has a bazillion of friends, then the chance that he actually names me as a friend out of these k is fairly small. And that could generate these lower percentages. And in thinking about this would suggest that where you might see lower percentages of bilateral links by degrees. So it's something that might be interesting to look at. I should also note, and Jan, I think, said something about this as well, that thinking about correcting for measurement error is incredibly important. So there's one very nice paper by Chandrasekhar and Lewis that thinks about measurement problems that are due to sampling of a subpopulation, but you could also think about misreporting. It might be that my hand just trembles, and when I have a friend, I actually forget to mention them, or sometimes I delude myself that Adam is my friend, but in fact he doesn't like me, and so on. And the truncation problem. So there are many issues here. And thinking, we haven't gone very far in either correcting for these statistically ex post, or thinking about techniques that would eliminate these problems or at least mitigate them. And that's a dimension that I think from a methodological perspective would be good to advance on.
Given all this, 60 to 70% is high. It's high, in fact.
Yeah, you could calculate numbers here if you assume something about the network. Okay, so I'm going to tell you about one of the simplest experiments of the type where you have an organic network and you run an experiment on it. And this will be a simple altruism experiment that was run on the network. So the field data was a friendship network and a lot of individual characteristics that were elicited in an all-girls school in Pasadena. The experiments that we ran were a series of dictator games where the design used the underlying network structure. So again, initially we ran the survey of the population of 5th to 12th graders. The surveys were conducted in January, and a few months later we ran experiments only with the 5th and 6th graders. And like I said, there's an age group advantage because it's more likely that this is a fairly self-contained network. We pay, I'll soon show you, but I'll soon show you how the payments are done. That was a big issue actually with the school. How do you pay kids? We almost opened a little Amazon shop in the lobby of the school. All right. So in the surveys, we had 77% participation, which might seem low, but it's actually fairly high for surveys. So a survey with 50% participation is considered not bad. 95% there was 95% participation in the survey for those that took part in the experiment. So for the people who took part in the experiment, we actually have a pretty complete image of the network. And there was also a fairly high participation in the experiment. So there were only 5% absent. Now in the survey,
It says 5th and 6th grade, they still listen to what they are told.
yeah, they're pretty tame. They're American. Yes. They're not Israeli.
Okay.
All right. So here's what we elicited in the survey. So we got a bunch of demographic characteristics, their height, their age, the number of siblings, some psychological characteristics, confidence, shyness, extroversion, optimism, physical characteristics like hair color, eye color, whether they wear glasses, whether they wear braces. It's very cute. Many of them do. And network characteristics. So this, I'm not sure I would do it again in the same way, but this suffered from this truncation problem. So students named 5 friends. They also named how much time they spend with each one. We were hoping to get something about the strength of the ties. Unfortunately, some of these numbers didn't sum up to 24 hours or exceeded 24 hours, which
It's fine.
you can be with both. Yes, yes, yes. But that, yes, yes. All right.
They could be, 3 of them could be together.
Yes.
If I said that I spent 3 hours with you,
I don't remember the correlation. Yeah. It wasn't, for sure it wasn't perfectly correlated, but I don't remember. I don't remember the number. Yeah. Okay, but with respect to just the links, not the time, about 63% of the links were two-way links. And subjects reported anywhere from 2 to 5 friends with an average of 4.4 friends. So they didn't get up to capacity, which is comforting in the sense that we're not hitting this truncation constraint, but some of them did. So this is, there's not much to learn out of it, but just to give you an image of the networks, the size of the nodes correspond to the n degree, how many people actually named them as friends. Blue corresponds to Caucasian, black corresponds to Asian, red is mixed, and yellow is anything else. Yeah. Yeah. When...
I mean, you should color code the color.
Yeah, it's right here, the legend. Yeah. Okay.
So this is 5th and 6th together.
Right.
So can I guess the line goes like this or something?
Right. Like you can put a line right here. Now, this is an image of the entire school where each color corresponds to a different grade. Not much to learn out of it other than the fact that they're pretty clustered around their grades. So we're not going to use information about their connections outside of their grade, but this is just to show you that they're fairly individual, and I don't remember which one of these were the 5th and 6th graders. All right. So the experimental design actually follows a similar design by Mobius, Quochan, and Rosenblatt. As students make 10 consecutive decisions. And these are the simplest experiments known to men or women. They divide $6 between themselves and another student. And they're randomly chosen participants. So they do this for 10 people, but these 10 individuals are chosen in a particular way. So we chose 3 individuals that were direct friends, 3 that were second-degree friends, and 4 with a distance of at least 4. Oh, sorry, it should be at least 3. One decision was implemented at random using a 10-sided die. So we implemented only one of these, and the earnings were distributed the next day with additional unannounced $2. This is an artifact of working with kids. This was just not to hurt anyone's feelings, so so that they would always get a certain amount. We wanted to make sure that they could never think that, yeah.
So you're telling them the names of the recipients?
Yes. But they don't know who gave them money. So when they get back money, they don't know where it's from.
And that includes the $2. So when I get money, if I get $2, I think someone picked me even if
Exactly. And that was the intention. So here's what it looked like. So this is decision sheet, say number 1 out of 10. Hello, Dictory's name. Please choose how you want to divide $6 between you and Elizabeth. So you had to specify amount for you, amount for the other, and they had to sum up to $6. Nothing. They actually did. I don't remember the percentage. Yeah. 6 is still.
All
right.
Somebody writing 6 in both
Okay, so okay, so the design here reduces any likelihood of some sort of strategic reciprocity, and the idea is that we really try to make them unable to learn who gave them what, how much. So there was randomness in the selection of friends. There was randomness in which decision got implemented. They acted both as a dictator and a recipient and got some of this. Yes.
So the dictator doesn't know which.
Sorry?
The dictator does know which decision was
No, they don't. They just know they filled up 10
It's a
surveys.
proxy for doing all of them, except you don't have enough money. That's all.
All right. So first of all, let's try to explain the offer amounts using the attributes. So I'll just show you results for a bunch of attributes. So height, race, shyness, and popularity. Popularity is the only thing that's actually taken from the network. This is the in degree. The recipient.
No, I guess that each one participated roughly the same number of times as dictator and recipient, or not? Not necessarily.
Not necessarily. Not necessarily.
Because
So
then I thought that the 3, 3, and 4 came from the distribution of degrees, so that we can balance
no,
things out.
No,
So
we
some
did this with some simulations. I won't show them today, but yes. What's bothering you?
No,
Okay.
no.
All right.
It's, if you got that endogenously from the graph, the
No,
distribution
no,
of
this-
degrees, and then you figured out what will be the right thing, so more or less each one, you had
No.
some Latin square kind of arrangement
No,
where
no, we didn't
everybody
have.
participates
No,
roughly equally.
no, we didn't. We had to correct for that ex post. But yes, yeah. That's all I'll say. And we used some interaction terms. So I'll show you the regression results. So this is explaining the share of the $6 that is given. And all you should glean out of this is that essentially there are two things that seem to play a role here. So in terms of individual characteristics, they explain fairly little, and only the measure of shyness is actually somewhat has power, or is significant.
Is shyness self-assessed?
Yes, yes,
So you
yes.
ask
So
them
it's
what
yes, exactly, yes, and these are of course subject to an array of issues. Yes. The in degree is also significant, so there is sort of a popularity premium here. They get more, and this model doesn't have a great fit. So here's kind of the distance pattern that we observe.
So
So
a shy dictator is going to give more. What?
Yeah.
How big is that effect? What does it mean?
it's
0 to 7. What units?
so these are units of 1 to 5 of shyness, and so each unit of shyness reduces how much you give by 4 cents. It's not a lot.
4 cents. I see. So 20. So even between the most and the least, it's 20 cents.
Yes, if you believe the linear extrapolation, yes.
No, I just want to see the
Yes.
magnitude of it.
Yes, it's not big.
There are a lot of steps.
Hmm?
There are a lot of steps also.
Yeah. All right. So this is essentially the main figure I want you to kind of take out of this, and this is a figure of the average offer as a share of the $6 as a function of the social distance. And what's important to note here is that this is a declining curve. So this is the main thing, and in fact, I'll show you that it has a very particular structure, it seems.
So naturally there is 1.
Yes,
So then, so there were some people offered even more than 0.5.
right, right.
Okay.
Okay,
Okay.
okay? Everyone okay? All right. Oh, this is from the network. So I say that the distance between us is 1 if we're friends. The distance between us is 2 if I'm friends with Adam and Adam is friends with you.
So it's inferred.
It's inferred from the network elicitation. Yeah, we infer it.
So
Yeah.
it's not as subjective.
No, no. I mean, it's subjective only in the sense that they report to us their friends, but this is just a different way to look at the same data. It's the cumulative distribution function of shares as a function of the social distance, and you just see that they're nicely ordered in terms of stochastic dominance. All right. So you can actually estimate these things. So you can try to explain these by using different measures of both networks and a distance effect. So we try to estimate the function of the form delta dij to the gamma. So this is basically the distance between I and j to the power of gamma times delta. So we allowed it to be nonlinear.
So just, can you go back to the graph for a moment?
This one?
No, the previous one. So you get roughly each degree of separation is like $1 roughly.
I'll show it to you.
Half a dollar.
I'll show it to you in a second. Yeah, I think I have it. Yeah, so strangers receive about 17%. First degree friends receive an additional 36%. Second degree friends receive an additional 20%. Does this answer, is this what you were looking for?
Yeah, just like $2.
This is an additional to the 17%.
Exactly, so they're getting over 50%.
They're getting over 50.
Yes, so this is what we just saw in this figure. Okay. And so when we included these network characteristics, yeah.
Could we come back to the point of reciprocity? So why is this no evidence for reciprocity rather than altruism?
Well, it's just that we made it fairly. There could be some reciprocity motives here, but we tried to make it very hard for them because you don't know whether the other person is actually giving to you. You don't know whom you got the money from. It's very hard to infer anything here.
But you know that it's your friend.
Yes, but the reciprocity means that I'm reciprocating some action. I might be reciprocating something else. They've been nice to me in the past, and that might be the underlying mechanism for this effect. So if you call that reciprocity, that's in line with what we're saying here. But just due to the experimental interaction, we tried to rule that out.
Now, did you get strange numbers like 4.21? And then I could say, no, I'm the one that gave you 4.21 because I mean, after the experiment, again, you got a strange number which is high. So remember, when I can identify myself by saying, I gave you 4.27 or something, which is a strange number, which is bigger.
Yes,
it's bigger than 3.
Yes.
And I can say that was
yes.
3.
Okay, so we rounded all numbers to the next dollar.
Which would impress your friend?
Look, your friend, mine are mine, you know.
So we rounded.
So you rounded it to what? To full dollars or what?
To full dollars.
Still, but giving $4 is something that was probably rare, but it happened. Otherwise, you would get average about 50%.
Right.
And say, I gave you $4.
Wait, so
But you don't know because, sorry?
they didn't get like dollar bills, right? Because otherwise
They did.
Just
No,
give
but
you
they
a
got
dollar.
it. But they saw the number. No, they saw how much they got. Then
I mean, I can pay you if you want to impress you. I can just give you the money.
no, those are girls in 5th grade. Yes, I mean it's talking.
Yeah. You had a question.
How many sessions or how was the implementation of this game?
Yeah, we came to the classes on several days, and every time we had 10 girls sitting in the classroom, and we had them go through the process of filling out the forms.
And there is not like a contamination by sessions? If you've not done...
No, we did this in sequence. We did this at the same time, so I think it would have been very hard for them to do this because they were sitting in front of a teacher. So this was all happening with a teacher present.
No, but I'm saying one group of 10 persons in one day or by day.
No, it was within a day. We went there, we did this in one shot. So it was in sequence, and there was a teacher overseeing everyone. So I don't think this was a big issue in this case.
But they saw all 10 numbers, or I mean, they saw all the numbers they got, only one of them
No.
was implemented, or they saw only the one that was implemented?
No, they just got an overall amount with these extra $2 that they didn't.
So they have, they didn't see all.
No.
Same. They were recipients 10
No.
times.
No.
They only.
They
got-
have no idea how many times they were recipients.
And could well be that they got nothing just because they never. I mean, they participated in 10 times, but in fact, none of them.
Exactly.
was
Then they would get
selected.
$2. Then they
And
would
then
get
they just got the
$2.
$2.
Exactly.
I
Exactly.
see. So they have. So the feedback is very, very low.
Exactly. Intentionally.
What were they told this was all about?
Not much. Just an experiment. You know, we tried to be very vague. I don't remember exactly the phrasing. This was a while ago, but we didn't tell them we're trying to understand how this social distance effect. This we don't do.
And was it clear to them that that will not be revealed, that that data will...
Yes. Yes. Yes.
The fact it's clear to you doesn't mean it's clear to them.
So that's absolutely true, and this is always a
Because they
concern.
will, you know, they will say, well, that's what teachers say. but
Yeah,
of course also
so
tomorrow
we're-
it will be a big
Yeah.
table which will show.
So the advantage of working with U.S. schools relative to Israeli schools is that kids are tame. On the other hand, the teachers are not as lax. So we had to go through many iterations to get them to approve what we were saying. So this went under many eyes to make sure that this would be clear. If they, I can never convince anyone that subjects understood or anyone understands what I'm saying, but that's all I can do. Exactly. Yes.
Do you see a reaction after getting a high payment for some people?
I wasn't there when the amounts were given, so I actually don't know. So I just wasn't physically there when we did this part.
It's not really reciprocation, but it's like, oh, people are generous.
But you won't see that because you don't know.
You don't know. It's very hard to.
You got $10. You don't know if it came out of being recipient 10 times or being recipient 3 times.
Right, but
And you have no, plus the $2. So how do you know?
right, but you see that one day you got some repair that is higher than what you expect to get.
But you may have been lucky and been a recipient for many people and just been randomly assigned, right? So you don't know. I mean, $7 might come from 7 people or from 2. That's
Including, there is some information, right, in getting ones. You might get lucky this bit.
why don't we get back to it
This
later
was
because
run,
I want to
more than one day, or you ran it just once?
one
No,
day,
so there was
one
no-
day.
there
So
was no
this is
second
what
day. So it's only once you got payoffs and that
Exactly,
was the end.
exactly.
So you could say the next day, oh look, I got a lot. maybe
exactly.
I'll
So
check
this
again.
was just done. We came in
So that
and
effect
then
is not, it's not there.
yes.
Was it okay for the parents so that their children are receiving money for somewhere?
Yeah, that's what I was saying about the Amazon shop. It took a while that we bounce. So when you work with children, at least in the U.S., it's they make you think about these things. So in the end, everyone agreed that this was the best way to reward them, but we did actually toy with the idea of giving them stuff or giving them tokens that they could then choose stuff.
So there was some interaction not only with school but also with parents.
No, it was mostly through the school, but the school, this is a private school for wealthy families in Pasadena. They care about what the parents think. They don't want to piss off the parents, but
And also the $6
Yeah.
was not significant
all right, okay.
to the.
All right, so we saw the direct role of the networks, and we saw that personal characteristics didn't explain a whole lot. I just want to say something about their indirect effect on results here. So I don't have time to actually dwell on the homophily that we saw here. So another part of the paper actually deals with the formation of the social network in this school. But we do find evidence for homophily over a bunch of attributes. So children of the same race tend to connect with one another, of the same confidence, popularity. Popularity is not very convincing because these are inherently correlated. Also height. In fact, I think also braces. There are also many triangles in these networks. And what I mean by that is that 75% of the links are links between two people who would be of distance 2 without that link. Okay, so I'm linking to someone who's a friend of my friend. So this suggests that a kind of an indirect way that generates inequality. So this is one mechanism. I'm not sure it's an important one, but it's one mechanism. So what we see here is that if you have a majority attribute, that may entail more friends. Because people tend to be homophilous, it might be easier for you to find friends. Now, having more direct friends gives you more favors. So in this case, this is a very, very simplistic setup. So you know, one would need to study it further. But here you get more help from your direct friends. So this suggests a potential relationship between homophily and inequality through this indirect channel of the network formation aspect itself. All right. So the main insights from this is that the network structure has overwhelming power in explaining experimental results, and personal characteristics are strongly related to the network formation, but not directly related to the outcomes themselves. All right. There's a bunch of other work of this type, and it's growing by the minute. So there are a bunch of other studies on altruism and networks. There's a new very nice paper on trust on networks that uses this model of looking at villages in India and running trust games on participants. There is one study that I'm excited about at Caltech where we actually elicited all of the networks on the undergraduate students, but also elicited a battery of attributes from them. So risk attitudes, competitiveness, confidence, what have you, anything you can think of, basically, that's easy to implement. All right, so in the last 2 minutes, I'd like to just say one word on matching and social networks and how I think some of the techniques for matching might be able to be transported to social networks. So while this hasn't been mentioned so far, there is a rather deep linkage between matching models and social network models. So if you think about the one-to-one matching, so this is a matching between two groups of individuals, say men and women, or firms and workers, or children in schools, and so on, it's essentially a bipartite graph. So you can think about firms and workers work for firms, and firms employ workers, and essentially we get a very particular type of graph. So in principle, we could use the literature on experimental matching markets to study networks. And there is a rather evolved literature of this sort. And if I had more time, I would tell you about some experiments that could lend themselves here. So for example, when I talked about the emerging stability, the first experiment that I showed you today, where we looked at network formation, there are actually some more free-form experiments in the realm of one-to-one matching markets that assess when stable outcomes might emerge. And stability and matching is a very similar concept to stability in social networks. So in that sense, I think it might be useful to connect more of these two literatures. And I think I'll end here.